Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Abdul Muhaimin bin Abdul Razak. My metric numbers is B0422101111. I am the leader from Group K. Today, our group would like to present about Fluid 2 assignment and using the CFD simulation. Okay, next, this is my group members. First, Muhammad Daniel bin Muhammad Hadi, B0422101124. Muhammad Haziq Safwan bin Muhammad Saha, B0422100028. Dan Raja Alauddin bin Raja Adam, B0422100044.
Next, I will continue on with the introduction. This video focuses on laminar flow across a flat plate. We simulate the fluid motion in a laminar flat plate using CFD simulation. We also employ the boundary layer thickness approach from CFD. Prior to learning about laminar flow across the flat plate, we must first understand laminar flow. Next is the boundary layer. Boundary layer is a thin layer of fluid that develops close to a solid surface and is known as the boundary layer. It is at this point that the fluid velocity changes from zero at the surface to the velocity of the free-flowing stream further away. We then continue to boundary layer thickness. Boundary layer thickness is the distance of a fluid moves from a surface to a point where its velocity approaches 99% of the free stream velocity. It defines the area where the fluid gradually changes its velocity from zero at the surface to the free stream velocity. The thickness of the boundary layer grows with distance from the surface leading edge and is affected by the surface properties, flow rate, and fluid viscosity. Next is the theory of laminar flow. Laminar flow is a smooth, orderly type of fluid flow where the fluid moves in parallel layers with minimal mixing between them. In this flow system, which usually occurs at low velocity or high viscosity where viscous forces dominate over inertial forces, the fluid particles move steadily and follow predictable pathways. We then continue to laminar flow over a flat plate. Laminar flow over a flat plate is a type of fluid flow where the fluid moves smoothly and steadily over a flat surface. The boundary layer of fluid close to the surface gradually changes velocity from zero at the surface to the free stream velocity further away.
I will explain about objective. First, to learn how the boundary layer forms and grows. 2. To determine the thickness of the boundary layer. And 3. To identify the circumstances that lead turbulence. And now, what is a computational fluid dynamic CFD? The category of fluid mechanics known as computational fluid dynamics CFD solve and analyze fluid flow issues using numerical technique and algorithm through the solution of complex mathematical formulas known as the Navier-Stokes equation, which characterize the motion of fluid particles. CFD model the behavior of fluid and their interaction with surface in a variety of applications, including environment engineering, chemical processing, weather forecasting, and aerodynamic. Computational fluid dynamics CFD enables scientists and engineers to visualize fluid flow, forecast performance, and optimize design through computer simulation. Why use computational fluid dynamics CFD? First, CFD allows analysis of multiple design options, allowing for the optimization of form, material, and system to enhance performance, efficiency, and safety. Second, CFD gives accurate and comprehensive information about fluid flow, pressure, temperature, and other variables at every point in the system. And lastly, complex fluid flow issues that would be challenging or impossible to investigate experimentally can be simulated and resolved with CFD.
Hello everyone, my name is Daniel and I'm gonna show you how to do the CFD simulation. Firstly, open Workbench and click Fluid Flow Fluent, right-click Geometry and click New Design Modeler Geometry. Once open, click Sketching, change Major Grid to 0.1, minus Step to 10 and Snap to 1. Okay, once open, we draw a rectangle, change the dimension based on the info given, click Generate Sketch and save the file. Okay, next we're gonna mesh the sketching. For meshing, generate mesh for the face, insert 3 edge sizing, 1 for top and bottom and 2 more for left edge and right edge. Insert the number of division to 50 for top and bottom edge and 60 for the rest. Click generate mesh and save the file. Okay, next we're gonna assign names for the meshing, edge sizing, sorry. For names, it's simple. Right-click the surface and choose Create Name Selection and name it Airflow. Do the same thing for left edge and right edge and also the bottom edge. Name it Inlet, Outlet and Plate respectively and save the file. Don't forget to add on the top edge as well and put it as far field pressure. After saving the file, click Setup and wait until the Fluent Launcher to open. Once it's open, click double precision and choose for process. For parallel flow, now press check and when there is the word done on the console, it means it's a good check. Click model and choose Lamina. Next, go to materials, click air and change the value of density and viscosity to 1 and 1 exponential -4 respectively. Click boundary condition, click inlet, change velocity to 1.5, click far field pressure and change type to symmetry. Click method and change it to simple. Now go to monitor and click residual, change all the value to 0.000001 and click OK. Now go to initialization, change the standard initialization and select inlet for compute and click initialize. Click run calculation, change the number of iteration to 1 million and click calculate. Now continue with the solution. Firstly, click graphic and right-click contour and change to velocity and bonded coloring. Click save. Secondly, click vector change the scale to 5 and style to arrow. Click save. Lastly, select path line, choose the inlet and click save. Now save the file. Click contour, choose the location to symmetry 2 and number of contour to 50 and click apply. Then change the variable to velocity and click apply. Next, click chart, press OK and change the X and Y axis to velocity U and Y respectively. Click insert, location and choose line. Change point 1 to 0.3 and 0. For point 2, change to 0.3 and 1.5. For sample, put 100 and click apply. Lastly, click chart 1, choose data series and change location to line 1. Save the project and you're done. Thank you.
And then data result, data 1 and data 2. Velocity, magnitude. First, fluid flow velocity increase and maximum. Second, fluid velocity is 0 because friction between fluid and wall.
Okay, then this is the result and data for data 1 and data 2. Velocity data 1 is increased and remaining constant at 1.5 meter per second. Velocity U data 2 increase and remains steady at 2.5 meter per second. Okay, lastly, the related result with the theory. For velocity magnitude, under laminar flow condition, this profile shows the velocity distribution within the boundary layer. According to our contour, fluid flow velocity increase and peaks near the flat plate. About the velocity plot, the velocity distribution plot on a flat plate depicts the change in fluid velocity across the boundary layer from the plate's surface to free stream velocity. When a velocity map is used to depict laminar flow on a flat plate, it displays a parabolic curve that gradually increases the distance between the plate surface and the free stream velocity. Our finding revealed that the velocity plot diagram at the y-axis shows that velocity u increase while remaining constant. Okay, so that's all from our group K. Okay, then thank you.